Testing, testing, 1, 2, 3. This is Chapter 9, Section 9-1. This is recording number 4. Okay, so here's example 9-1. And as I've said so many times, these are just metaphors for more important, interesting questions. The exact same tactics, the exact same technique would be used for all kinds of things that are perhaps more important and more interesting. In any event, we've got a study that used 2 random samples of 35 persons each. Okay, so we have 2 samples, N1 and N2. So where's our formula? Right here. So we have N1 and we have N2. And the average amount of time in a certain age group spent per week on leisure activities was 39.6 hours. And the people in the other age group is 40, a different age group spent 35.4. So we have an X bar 1 and we have an X bar 2. Assume that the population standard deviation for the first group, for the group number 1, is 6.3, and the population standard deviation in the second group is 5.8. Okay. So we're going to make our alpha 0.05. That is our error budget. That's how often we're willing to be wrong. Can it be concluded that there is a significant difference in the average times that each group spends on leisure activities? Okay. So sometimes these concepts of are you in a population or a sample or whatever get to be confusing, to say the least. Okay. So what we're trying to decide here is whether this age group, 26 to 35-year-olds, is it the same population as the age group 46 to 55? So just think about that in terms of, change it to something that makes more sense to you, like the people that took the medication versus the people that didn't take the medication. Are they the same population? Is there a significant difference between those two populations? People that took the medicine, people that did not take the medicine. Well, we cannot possibly test everybody that's in either of those two populations, right? I mean, it would be impossible. So what we do is we take a sample from each of those and we run the statistical test. Now, if there is a difference between them, between the two samples, statistically significant difference between the two samples, then we say the two populations are different. If, on the other hand, the null hypothesis is true, if it's the same population, the two groups, despite their age or despite whether they took the medication or didn't take the medication, whatever it is that you're looking at, if the mu's are the same, then we say it's one population. So it gets confusing. I know when I first started studying this, I was confused by why we used mu over here when we're talking about samples. But the idea is that the samples merely represent the populations. We're really talking about populations, whether or not the samples came from two different populations or whether the samples came from the same population. If I were the king, I would change the notation, but unfortunately, I'm stuck with the notation that they use. All right, so in any event, we've got a null hypothesis that the mu's are the same. Mu1 is equal to mu2. The null hypothesis is this one. The alternative hypothesis, the research hypothesis, is saying they're not the same. Mu1 is not equal to mu2. Okay, so as before, we do exactly the same. We have an alpha, and this is a two-tailed test because we're saying that they're not the same. Alpha is equal to 0.05. So if it's 0.05, that means that 2.5% of the time will be wrong over here. 2.5% of the time will be wrong over here. The appropriate z value is plus and minus 1.96. Okay, so that's our critical values. Please take my advice, draw the cartoons. Please take my advice, write down the formula every single time. So you write down the formula to get your test value. So z equals all of this, and that is equal to, and now that you've written down the formula, all you have to do is plug in the numbers. It's very trivial. X bar 1, X bar 2, that was given to you. Here's X bar 1, here's X bar 2, and so forth. So we have all the stuff that we need to plug in. And what is usually going to happen is the mu1 take away mu2, this term right here is going to be 0 because our null hypothesis is that they're equal. So you crank out all of these numbers and you come up with this. 2.90 is the test value. Go to your cartoon, your 2.90 is over here. It's past the critical value, therefore you reject the null hypothesis. So the summary would be, there is enough evidence to support the claims, to support the claim that the means are not equal. In other words, the average of the time spent on leisure activities is different for the two groups. So another way of saying that is to say that the population of people aged 26 to 35 is different from the population of 46 to 55. And this exact same technique, everything we just did, is equally valid if you were talking about something of more consequence. If you were saying, what do you think the chances are of somebody aged 26 to 35 of dying from COVID-19 compared to people that are in the age group of 46 to 55 years old? You could find a mean for both of those. You could find the standard deviations. You could do all of these things, and you could decide, is there a difference between in the what's called the mortality rate. Mortality rate is the rate of people dying. So is there a difference in the mortality rate of this age group compared to this age group? You would use this exact same technique to make that decision. Okay, so this is the so-called traditional method. In the previous chapter, in chapter 8, we also learned how to do it with so-called p-values. Remember, the p-value, p stands for probability. So the idea that what's the probability of getting, where'd it go here? What's the probability of getting this particular test value, or even more extreme test value? So like, what's the probability of getting 2.9? Oh, I'm sorry, here it is. What's the test value? Yeah, 2.90. So the p-value technique says, hey, what's the probability of getting this test value, 2.90, or even more extreme, going further down the curve, what's the probability of getting that result? If that result is so unlikely, if you say, oh my gosh, that is so unlikely, that probability of getting that is so unlikely, I'm going to reject the null hypothesis. So that's the concept. We don't have a critical value like we do in the traditional method. We just calculate the probability, and then we say, hey, that's so unlikely, I just don't believe it could have happened. So that's the essence of that. So let's see the details here. Okay, so if the test value for a two-tailed test is 2.90, which it is, the p-value obtained from table E is 0.0038. So we did that before. I don't think I want to try to do that again, if you don't mind. It's just look back on our previous work on that. Okay, but he kind of walks you through this right here on how to do that. Okay, so here's the steps. You state the hypothesis, compute the test value. You do not compute the critical value. You're not going to use the critical value when we're using the p-value test, or the p-value method. Okay, and then you make your decision. Okay, now example 9.2 looks really hard, but it really isn't. It's just extremely tedious, and I really wouldn't even necessarily ask you to do this. It's just too much busy work to calculate these parameters here. Okay, so I'll let you read that yourself. Okay, and what you're going to need, of course, is the x bars, and you're going to need you're going to need the x bars, which you have to calculate, and then the sigma sub 1, sigma sub 2 is the other part of this. Okay, to give you the variance, the sigma sub 1 squared. That was given to you in the problem. So this is kind of the tedious part right here. It's easy enough to calculate, but a headache. I wouldn't waste your time on it if I were in your shoes. Now, if you did do it, just go to one of the website calculators and just plug in those numbers. Okay, so, always the hard part is to figure out what the null hypothesis is, what's the alternative hypothesis. So the hypothesis, what he's thinking, his claim or his alternative hypothesis is that the average number of sports that colleges offer for males is greater than for females, right? Okay. So our random variable here is the number of sports. How many sports? Baseball, football, basketball, volleyball, water polo, those kinds of things, okay? So the number of sports is the random variable. So these are the various colleges that they went to, however many colleges this is, and you come up with the actual numbers, okay? All right, so in any event, H sub 1, the alternative hypothesis is that the average number of sports for men is greater than the average number of sports for women. So you calculate this x bar and this x bar 1 and x bar 2, and then you plug into your formula, okay, and what do you get? You get 1.06. Okay, now this little asterisk here is just telling you, be surprised if your result is slightly different because there's going to be rounding errors and so forth, okay? So anyway, you got this 1.06. So now we got to find the p-value that corresponds to this. So I'll go ahead and help you with that. Just do one more of these. Okay, so we just calculated that the z value, the so-called test value, is 1.06. So here's the table of the z values, the cumulative standard normal distribution, okay? So 1.0 is this row right here, 1.0, then you come across here till you get to right here. Boy, it's hard to see this. So 1.06 is this guy right here. So the 0.06 adds to the 1.0 gives me 0.8554. So remember what that means. 0.8554 means that to the left of that z value is 0.8554 of the area, okay? So that's the area to the left. Well, what's the area to the right? It's going to be 1 subtract 8.554. So that's what the author is saying right here. He says 1 subtract 0.8554 is equal to 0.1446. So in other words, that's the p-value, the probability of getting the probability of getting 0.1. He doesn't have it labeled here, but that's this guy right here. The probability of getting the critical value of 1.06 or more going this way is 0.1446. So in other words, it's 14 point something percent. Okay. So I wish you would have written that in there, but right there, that's the z value of 1.06. That z value of 1.06, that corresponds to this difference here, the 8.6 take away 7.9, that corresponds to that difference, of obtaining that difference. So there's, what it all boils down to is the probability of getting that much of a difference or more is from here to here. That is the probability. So it's 14.4%. Okay. So now the question becomes, you say, well, listen, just by random chance, it's the way the universe operates. By random chance, there's a 14.4% chance of getting this much of a difference right here, this delta right here, this difference, just by random chance. There's a 14% chance. So am I going to reject the null hypothesis when there's a 14% chance of it happening just by random chance? Well, no, I'm not, because I want to be reasonable about it. And you always want to have at least an alpha of 10%, if not 5%. So that's why we do not reject the null hypothesis if we're going to use the 10% level of significance. Now, if you were a talk show radio host, you don't understand how to do hypothesis testing, what you might say is something like, oh my God, of course there's a difference. There's only a 14% chance of this happening. by random chance. Well, okay, then change the rules. Go write your own book. But that's not the way that we do it in a scientific environment, okay? So that's the end of this tape.